Good day, everyone, and welcome to this Lightbend webinar for July 30th, 2020, titled Akka at Enterprise Scale, Performance Tuning Distributed Applications. My name is Oliver White, Chief Storyteller and MC at Lightbend, and joining me is my colleague Nolan Grace. Nolan is a Senior Solution Architect at Lightbend. He enjoys solving problems, working with distributed systems, and wine tasting, as do I. While I introduce today's session, which has a lot to cover and should last the full hour, I would like to ask our audience a quick poll question. Which Akka modules are you using? So if your applications aren't consistently breaking new performance records, then you're really not alone. How do you even go about doing that? We've seen our clients like Starbucks, HPE, and PayPal find huge success with the Akka toolkit for their enterprise scale apps because of their really extreme performance requirements. So using Akka, PayPal processes over 1.5 billion events per day. HPE keeps track of over 20 billion virtual sensors across their global data centers. And the Starbucks inventory systems and mobile rewards app power the Starbucks-related activities of tens of millions of people every day around the world. And what we've learned from these giants is that when it comes to squeezing out the best possible performance of your Akka system, the secret is using two particular modules in tandem, specifically Akka Cluster and Akka Streams. And that's what Nolan will be showing us more about today, the features that will help you push your application architecture to the next tier of performance. So we will do a quick review of the requirements for successfully creating a distributed reactive system architecture. We'll do a deeper dive into two specific modules in the Akka toolkit, as I mentioned, Akka Streams and Akka Cluster, and actually how they complement each other. And then we'll finish up with examples of Akka Streams and Akka Cluster, plus some other modules like Split Brain Resolver, and have a little bit of code there to help you use in your next project so that you can start to test out what it looks like to max out every node that you can, and also test out some of the recovery features. All right, thanks for your poll questions or poll responses. Just a few final remarks. Today's webinar is made possible only by Lightbend's hundreds of happy customers, especially our client Brighthouse Financial. They're actually one of the largest providers of annuities and life insurance in the US, and they have two positions available for lead principal software engineer, focusing on folks with extensive experience with Akka and Scala or Java. You can find more about these positions under jobs.brighthousefinancial.com and just do a search under the keyword Akka. I'll put that in the chat in a moment. As always, this webinar is being recorded and it will be made available to you for replay next week. If you have questions for Nolan today, feel free to add them to the GoToWebinar control panel, and we'll plan to get around to them in the Q&A part of today's session. As always, if you're an existing subscriber, then you are aware that you can go directly to our expert engineers through the customer portal, and that's where you can ask any additional technical questions about Akka Streams, Akka Cluster, and other Lightbend technologies, as well as what-ifs, how-tos, and certain things about best practices. Well, that's all I have to say, so I'm going to shut up, hand it over to Nolan Grace. Nolan, thanks for joining us today.
Thank you for having me. And as always, Oliver, exceptional introduction. So to just jump straight in and start going through all of this content, because there's a lot of interesting things today that I want to run through that hopefully will help everyone on the line become better Akka developers and just better architects in general. So you gave me a great introduction, Oliver, but to add some extra stuff, like Oliver said, my name is Nolan Grace. I'm a solution architect at Lightbend. And what that means is it puts me in a really interesting role to be able to go around to a lot of different organizations in a very short time period and see how people are using the Akka tools, how people are building reactive applications, and what kinds of techniques are working and what kinds of things aren't working. And over the last couple of years, I've been able to see some really interesting patterns for what really successful reactive projects do similarly, and these are the practices that we're really going to be talking about today. Another thing I should actually add to this slide is that if you want to look at some of the code that I've been writing, my GitHub handle is just Nolan Grace. So feel free to look me up there as well. So first and foremost, for those of you who, Lightbend has a lot of different open source offerings. We've got Akka, we've got Logum, we've got Play, and then we also have new tools such as Cloudflow and CloudState. Today, we're really going to be focusing specifically on Akka and, as Oliver mentioned, Akka streams and Akka clustering. But for those of you who are not super familiar with Akka, do not fear. We're going to start a pretty high level and then accelerate into some of these extremely cool patterns really quickly. So first, let's start out with some cool pictures and some cool cars. So as I was kind of working on this session, the metaphor that I really liked for talking about some of these concepts really is building performance vehicles. How do you tune your high performance applications in the same way that a pit crew would tune a high performance car? And the Ford GT is just one of my favorite cars of all time, and I just think it's a very cool one. So throughout this session, I'll be talking about a lot of these reactive patterns and how they kind of have parallels to performance vehicles. So starting from square one, reactive architecture. I absolutely love the concept of reactive architecture because it is so simple, and it's not targeted specifically even at technology. These patterns are really about how do you build better interactions with your customers. And so everything reactive can also be applied to how you should be communicating with people via email, how you can be working with your customers personally or your friends, things like that. But to go through each of these, reactive architecture starts at being responsive. You want to make sure that first and foremost, that if you get a request from another system, if you get a request from an external user, your application does the absolute most it can to respond to that request. Then beyond responsive, we have on the left side there, elastic. So we want to make sure that as requests from external systems increase significantly, that we're able to scale up in order to maintain responsiveness. But then the actually more difficult part of that is to be able to scale back down after traffic starts going back down. And that's just a cost-effective manner of building applications. And then on the right side, we're talking about resiliency. In the case of failure is always going to happen. Things are going to get lost. There are going to be network partitions. Nodes are going to crash. We need to maintain responsiveness even in those situations. And then last, at the very bottom, message-driven is really it's a technical implementation detail, and the only way to really get the best of all of these features is to build applications driven by asynchronous message passing. Synchronous communication or using getters and setters on all of your objects just is not a really highly scalable way of building software. So this is a lot of very abstract patterns, and as I was trying to think about some of this stuff for this session, I came up with a massive list of more specific details that I think a really highly tuned architecture needs. And as I slowly whittled down this list that was initially like 50 different things, I was able to kind of group some of the things together, remove some things that weren't as important. And these 5 things are really it seems like all of the customers that I've worked with over the last couple of years, all of the systems that I've built, all take great advantage of these specific elements. So, end-to-end monitoring. This is one we'll talk about a lot, and it's really important because it's impossible to make anything better without understanding what the current state of that thing is. You need to understand where your system is, and you need to be monitoring your system actively in order to decide where you're going to spend effort to make it better. Number two, efficient resource usage, making sure that we're threading, we're using the right amount of CPU and memory for all of the right pieces of our application. Scalability, this is really similar to elasticity when it comes to reactive architecture, but when we need to get bigger, how do we get bigger? When we need to save costs, how do we get smaller again? In-memory speed, taking advantage of caching and memory or objects in memory, and then self-healing. Catastrophes happen, we need to heal. So you can see a lot of these technical details, and I'll talk about each of these as they actually apply to the technology. But the point being that reactive architecture is really very, very abstract, and I want to take these important 5 concepts and actually talk about how you implement them in using Akka, and specifically Akka streams and Akka clustering. But I also want to point out, most of all, end-to-end monitoring is absolute. If you're going to do only one thing in your reactive architecture to try to make it better, monitoring is the most important thing, because none of this stuff matters. No tuning, no messing with your app, no making changes it's really difficult to actually make positive progress in your application if you're not constantly taking benchmarks of how your application is actually performing. And so end-to-end monitoring is definitely the most important thing you could possibly do to build better software. So now let's get into the meat and potatoes of how we actually get this done. So enough of the abstract ideas. Let's look at some concepts in Akka and look at some actual code to understand how we take advantage of these tools. And I'll also, before we kind of jump right in, one of the really worrying things about me in the world of reactive systems, and especially the Akka landscape, is that people don't take advantage of all the tools that they possibly can. Some of these things do get very complicated and can be difficult to really get the most out of and to truly understand. And so when it comes to Akka streams and Akka clustering, I've noticed a lot of organizations that I've worked with will really focus very highly on one or the other of these modules. And as is very frequent in the Akka documentation, Akka is a toolkit. It gives you a bunch of tools that you can use for the right use cases. But Akka is a toolbox. You should be using more than just one tool. A hammer doesn't solve all problems. And just as Akka streams is really only a piece of the puzzle when it comes to building reactive systems. So today, hopefully by the end of this session, everyone will have a really much better mindset of, if you're an organization that really focuses on Akka streams, how to start taking advantage of Akka clustering and state in your streams. And then on the other side, if you're an organization that really has a really persistent entity-focused architecture, how do we start using streams to better organize work coming in and leaving your system? So first, for those organizations that don't highly focus on Akka streams, let's start at the very beginning of building an Akka streams application and why Akka streams is valuable. So in my opinion, and this is a very bold statement, Akka streams really is the best tool in the Akka toolkit. It's extremely useful and extremely powerful, and it really gives you the ability to build out the entire logic of your application, everything that needs to happen. And Akka streams will take care of making sure that resources are correctly allocated to all of those stages. So we're looking at this kind of simple diagram here. So an Akka stream is really just made up of a bunch of different sources, flows, and sinks. So sources, they push information wherever that is. A list, potentially it could be reading from some sort of external data source. It could be HTTP requests coming into your system. Those sources feed data downstream. Flows have inlets and outlets, so data is coming into them as well as going out of those flows. And then sinks are really the end of your chain that is kind of the last element in your sequence. And what's really nice about Akka streams as opposed to other streaming tools is, first, it's really simple and lightweight. When a lot of people think of streaming, they think of these big complex streaming engines like Apache Spark and Apache Flink. Akka streams is very different from that. It's not a big engine for processing massive amounts of data. While it can be used for that, it's really just a small element that you should build your applications around. All of your logic should really be set up in these streams, and that way, well, you get backpressure throughout your application. So what backpressure is actually in Akka streams, rather than all of your stream constantly pushing information downstream to all of your elements, Akka streams will actually do a pull-based model. So the first thing that happens is your sync will actually, when everything comes up, your sync will, you see these little dotted lines that I have here. It'll actually request from the flow to say, hey, I've got enough bandwidth or I've got enough CPU in order to process a message. Give me a message. And then if the flow doesn't have any messages, it'll pull one from the source. And so by using this pull-based processing, you're able to make sure that no slow downstream operators are ever overwhelmed by fast upstream operators. And you're able to make sure that machine resources are really well distributed throughout your application. So there's no reason to use an enormous amount of CPU on one of your sources if the downstream flow isn't able to keep up, because the flow is just going to get overwhelmed and your app's going to end up crashing. So you've just wasted CPU in your source that should have been used for your flow. So Akka streams makes that really easy, and you really don't have to think about those things. You just build the logic in these sequences. And so we'll look at some of this code of how you can actually do this. So really simply, let's say we have an operation in the middle. So we have a list of data, 1, 2, 3. We've got an operation in the middle that's really CPU intensive. It's going to be really slow, and we want to make sure that that occurs and then moves into the sync. This is all the logic that you need to actually code that concept. So list 1, 2, 3 in the source. We do a map with this CPU heavy operation, and then to sync.ignore. Really simple and straightforward, and really what actually happens in the background and how this actually works and how durable and performant it really is it really impresses a lot of people. But now let's say, well, you can see this box around all of these operators here, the source, CPU heavy, and the sync. That box is actually a thread. So typically when you just build your application like this, or your stream like this, it's actually going to execute on just one thread. And so now if we want to start introducing multiple threads, we want the CPU heavy operation to occur on a different thread than the sync. Well, how do we implement something like that? The power of Akka streams is it gives you this really, really simple way of creating real kind of magic with your application. Introducing, asynchronous boundaries, multiple threads, high parallelism, high concurrency, pipelining. It gives you a lot of these amazing tools without you having to worry about a lot of the intricacies and how that works. You're able to simply just plug in .async right here, and Akka itself takes care of coordinating these two threads and making sure that information moves correctly from one of the threads to the other thread. So in this model here, we actually, we've introduced an async boundary. And so we're able to move, so this source and the CPU heavy operation occur on one thread, and then the sync happens in the other thread. And, this may seem, so this is really simple, but something that really does surprise a lot of people is that, you don't always just want to add asyncs between every single operation in your stream, because there are significant performance increases of having lots of things running on one thread. So by adding an async boundary, there's a performance hit, but depending on your application type, maybe that's exactly what you need. Another great pattern for Akka streams is actually being able to use something called map async. So let's say rather than this model here where we have 2 threads running, I just want these CPU heavy operations to occur on different threads. And then when they're completed, I want them to move forward. Really simple in Akka streams. So all you need to do, so same as before, we've got our source with 1, 2, 3. Now, if you use map async, you're able to give it a level of parallelism. How many of these operations do you want running at any given time? And Akka streams will actually take care of creating these futures. So these CPU heavy operations are actually going to go, depending on how you set up your execution context, that they'll execute on different threads. And they won't affect the actual operation of your Akka stream. And every time those futures complete, they'll get pushed downstream to the sink. So if I wanted to have 10 of them running at once, I would just change that 2 to a 10 instead. Extremely simple, extremely powerful. And what's also really impressive about this map async is it will keep your ordering guarantees. So if your CPU heavy operations could potentially, if we have 10 of them running at once and they might not always complete in the order that they came in, Akka streams will actually make sure that they still do move downstream in order. Now, if you just want to go as fast as you possibly can, we'll show something along those lines later. But for now, this is, well, hopefully just from a couple of these slides, I've been able to kind of talk about, I've been able to show kind of this simple API of how you can take advantage of Akka streams, and you can build really, really complex, really interesting streams that perform extremely well. So by building your application in this kind of streaming, this streaming way of doing things, what you actually get is a really nice dashboard into how your application is working. So by if you had a bunch of operations that could occur in any kind of order, they could sometimes happen this way, sometimes happen that way. It becomes really difficult to start understanding what sequence of events is really causing negative performance in your application. So by building your application really centered around streaming, and then using tools like Lightbend telemetry to monitor those streams, so you're able to monitor a total stream performance and then the actual performance of every single operation in that stream, you get a really, really nice dashboard into your application, just like a your speedometer and all these metrics in your automobile. It's really difficult to know what's really happening. It's hard to drive without these things. And same thing with building an application. It's hard to know what's happening in your application if you don't have these metrics. And it's especially hard to make your application better if you have no idea what's going on. And so Akka streams, first, it gives you this by building your application in this way, it makes it a lot easier to measure. And then also, number 2, it gives you just out of the box efficient resource usage. You know that by building your application in Akka streams, you're never going to end up with memory overflow problems. So slow operations will never messages will never pile up and overwhelm downstream operators. And you know that your application will go as fast as it possibly can go, given kind of the threads that you've set up. And that's just something that comes out of the box with Akka streams. And as you get better with Akka streams, you can build even more highly performant things. But the safety in Akka streams is that you're not going to end up in a situation where you're crashing your system, because backpressure really protects you a lot in high scale situations. So next, we're going to talk about Akka clustering. So I don't anticipate that anyone reads this information on this slide. I'm going to be going through all of this in a minute. But I just wanted to put it here for people who actually might see these slides somewhere else. Akka clustering is about adding more nodes. first and foremost. So you can't build a distributed application that's not distributed. You need multiple nodes, and Akka clustering gives you the ability to do some really special things once you have more than one node. So for example, Akka clustering will take advantage, will make sure that as nodes come in, they're added correctly. So this is really, as your application scales, as your traffic goes up, we need to add more nodes, and we need to make sure that this node is able to get assigned work and start collaborating with the other nodes in this cluster efficiently. And so Akka clustering takes advantage of that really, really well. And as you're adding nodes, those nodes join, they become partners, and then all the other nodes in the cluster can communicate with that node really, really simply, as if it basically was just one node. So you're able to build these distributed applications, but as long as you follow the good Akka, asynchronous message passing practices, then you really just think of it as if it's, a one node application that's able to scale like crazy. And so that's really, back to our car metaphor, that's your acceleration. We're building an app that can go from 0 to 60 as quickly as possible, and Akka cluster makes that simple. Same thing with stopping. Our car metaphor, stopping is extremely important. I think we can all agree on that. And if there are catastrophes, if nodes go down, or if we simply want to start making our cluster smaller because we don't have as much traffic anymore, we're getting off the expressway and we want to slow down, Akka clustering also makes sure that as these nodes go down, the rest of the nodes are able to continue processing well, even with that node gone. So if there's data cached on that node, if there are streams running on that node, Akka clustering is aware of that and is able to gracefully down those nodes. And that's, Teslas just have really good brakes in general, but they also have, some really cool self-driving features that will, slow them down in the case of critical failure. And, that's also comparable to some sort of split brain problem. So the Lightbend split brain resolver, which was actually open sourced recently and is just part of the, I guess that might be interesting for some people to know. Historically, there was a commercial tool called the Lightbend split brain resolver, and it was able to make sure that we could enforce consistency in Akka clustered applications. Recently, that tool has actually been open sourced, and it's just part of Akka now. So you can take advantage of Akka clustering and really use these powerful tools and still be sure that your application, even in the case of a split brain problem. So so this red line here is an example of a network partition. So if for some reason we've got a 5-node cluster, and all of a sudden there's a network problem and 2 of the nodes can no longer talk to the other side, the split brain resolver has a really complex logic setup that will down the correct side of this cluster. So if you do have in-memory entities or there are changes to distributed data occurring on both sides of this partition, potentially data can get out of sync and it can cause real catastrophes in your application. So, in the case of split brain resolver, it'll actually down the 2 red nodes and make sure that the other side can continue processing effectively despite that critical failure. And so those are the really, great things about adding and removing nodes that Akka clustering gives you. But, really it's the tools inside of Akka clustering that are important. So of course you can build stateless microservices, using just pure Akka streams. But this is the story that I'm really trying to tell here is there's a level beyond Akka stream stateless microservices that's really amazing. It's really the tool that really differentiates good reactive applications from exceptional reactive systems. And that's these tools I'm talking about. First, Akka cluster sharding. In our list of important things for building these high performance applications, in memory state, there's tons of systems that are coming out, especially in big data processing, and they always tout, Apache Spark is better than Hadoop because it's now able to take advantage of data in memory. Data in memory is significantly faster than having to constantly read data out of a separate database or out of or off disk. And so being able to leverage Akka cluster sharding actually will let you build applications that have strong consistency. So this is a really important thing for a lot of organizations, is making sure that our data is strongly consistent. If a user makes a change, that change needs to, show up immediately. It can't, show up later. So I'm a big fan of eventual consistency in a lot of systems, but if you need strong consistency, Akka cluster sharding is the way to go. We're able to back up this data, so these in-memory entities are actually able to become durable using event sourcing. So every time you make a change to user 1, that change gets persisted to a database in event sourcing as opposed to a CRUD model. So we're able to use really nice features in Cassandra or distributed databases as opposed to relying on a relational database, which gives us even better performance. But one of the problems with Akka cluster sharding is that these entities may not always be local. So requests could potentially come in so you could see the node that has user 3 on it. An HTTP request may come into that node saying, hey, I want to make a change to user 1. Well, user 1's not on that node. So that node Akka cluster sharding takes care of all of this for you, but it still has to forward that request over to the node that has user 1 on it. The actor on that node for user 1 processes that request and then sends a response back to the user 3 node and then back to the user. So the trade-off of being able to use cluster sharding and getting strong consistency is that potentially the data may not always be local. If it's absolutely necessary that, and in a lot of cases it is, that the data is always local, so we want to focus more on high availability as opposed to consistency. For those of you who are familiar with the CAP theorem, there's another tool for that, and that's called Akka distributed data. And things like leaderboards. So we're playing a video game, and we want to know, the rankings of everyone who's in our competition right now. Well, leaderboard, we're able to synchronize this data across all 3 of these nodes. And if two changes come into different nodes at the exact same time, both of those changes will be propagated through to all the other nodes. But there is a potential that one node makes a change locally that isn't reflected immediately on the other node. So Akka distributed data also gives you this amazing in-memory speed, but it's got tunable consistency, and the guarantee you get is that that information is always stored on the local machine that you have. So from our list at the very beginning are 5 points that are extremely important for building these amazing building really amazing reactive applications. Akka Streams gives you end-to-end monitoring and efficient resource utilization. Akka clustering also, there's some really nice features for monitoring when it comes to being able to monitor all of your nodes. But more importantly, from the clustering side, is clustering gives you scalability, adding and removing nodes. It gives you, in-memory speed of the data that you're working with, especially in the case of when you have durable state, something like user information as opposed to just messages. And number 5, self-healing. In the cases when we have network partitions and we lose a bunch of nodes, Akka cluster is able to keep your application stable. In the case where bugs or hardware failures or whatever could happens, Akka clustering is the piece that keeps all of these nodes coordinated and running consistently. So with all of this, there's been a lot of information so far, and I hope everyone on the channel is still with me. And I think this next part is really my favorite part of this session, because this is really the stuff that starts getting really interesting and really new to people that haven't seen it before. And it's really how do we create a really, really good relationship between using tools in Akka streams and tools in Akka clustering? And as you can see here, this is just an example of basically a stream running on one node, feeding data onto a stream in another node. But at the same time, how can Akka streams send messages to Akka actors that might be on different nodes? How do we, fan data from a bunch of front-end nodes to back-end nodes? There's some really, once you start using these practices, there's some really, really cool magic that you can do to build really complex applications, but the development of them is actually really, really simple. So for those who haven't read this page of the Akka documentation before, I would recommend going and taking a look. This is one of my top 10 favorite pages of the Akka documentation. Actor interop. And so this really is, so it's in the Akka streams documentation. It's given that we're using an Akka stream, how do we, communicate with Akka actors? And throughout the rest of these slides, I'm going to be talking about Akka actors. But as mentioned in the clustering section, Akka actors could be on different nodes. If we're using Akka cluster sharding, or if we're using distributed data, those things can be on different nodes. So we can be processing data from a stream and then talk to an actor on a different node, and that actor may send a message to another stream. And so we're able to code as if all of this is happening on one node. And this is really the power of a lot of these Akka clustering tools. We can code as if everything is happening on one node, but split everything up over many nodes. So to do that, it's really amazingly simple. So going back to another, so we've got our stream and we've got a source sending messages 1, 2, and 3. But instead of processing this message in a stage of our stream, I actually want to send these messages out to a Akka actor. And like I said, that Akka actor could be on a different node. And I want it to accept those messages and do something with it. And then I'm just going to keep going forward. So to do that, really simply, we're just going to have a map stage that does a tell. So in Scala, just using the exclamation point with an actor ref, we'll send that message over to that Akka actor. And Akka clustering, if you're using Akka clustering, will take care of routing that message all the way to an actor on a different node if you're using something like cluster sharding. And so in this case, we're able to have this stream, that could be processing massive amounts of information and just firing messages over to this actor. But the problem with this pattern is that there's a potential that, I'll mention that first. This actor that I have here, where it says actor, it actually could be many actors. So we could take information from these messages. So something like user ID or car ID. So potentially we could say, we're going to send these messages to the correct car actor in our cluster. But with this tell pattern, we lose backpressure. So as mentioned earlier, a great feature of Akka streams is this backpressure, the ability to not overwhelm anything in our system. This pattern here actually, though, could potentially overwhelm this actor. There's a possibility that this stream is able to go a lot faster than that actor. And one of the nice safeties about Akka is that in that case, it's not going to crash the actor. It's just that if the actor's mailbox gets full, then messages are just going to get dropped and lost. And sometimes that doesn't matter. So if an actor can't process something immediately, we might as well just ignore it and pretend like it never happened. But if you want to make sure that your stream will slow down based on how fast a actor or a pool of actors is going, you can simply just use the ACK pattern or the ask pattern. So the difference in Akka actors for a ask versus a tell is a tell will just fire and forget. It'll just send the message to the actor and it'll either get there or not. For an ask, we're actually sending a message to an Akka actor, and then we're going to wait for a response from that Akka actor. Now, in this Akka streams code down here, we're waiting for a response, but it's blocking messages moving forward in the stream, but this is not synchronous communication. It's still, we're not locking up threads. But our stream, if the message 1, we're waiting for a response from the actor, message 2 won't get sent until we get a response for message 1. And so this introduces backpressure where the Akka actor is able to, if no responses are coming back, then our stream is not going to send any more messages to this actor. And so by just switching from a tell to an ask and then having this acknowledgement that we need back from the actor, we're able to now introduce backpressure between an Akka reactive stream and an Akka actor that could be doing all sorts of things. Inside of that Akka actor, there may be another stream, or that actor may be sending messages to other streams to perform operations, and then eventually a response comes back. And so we're able to start introducing backpressure in a slightly different mechanism through lots of different pieces of our application, and potentially over network boundaries. Like I said, that actor could be on a different node. And so, as we'll get into it later, you could have nodes that are specifically responsible for doing certain things. And this would be the way of being able to send traffic over to those nodes. So, from this example right here, the other point that I forgot to mention is, I kind of did mention it. Only one of these messages is going to ever be over at this actor at any given time. But let's say, like I said, we're sending these messages to user actors, and we're sending each one to the corresponding user actor. So 1 goes to user actor 1, 2 goes to user actor 2, and 3 goes to user actor 3. Well, there's no reason to wait for user actor 1 to finish processing in order to go to, user actor 2. So if we want to have more of these messages being processed at once, and the order of them coming in doesn't correspond to how they need to leave this stream, then we can actually take advantage of map async unordered. So we looked at map async earlier, and map async is going to make sure that the order of the elements that come in the order of the elements that go out matches the order that they come into a specific operation. If we do unordered, then as these futures complete, they're just going to move forward in any order. So, as fast as they possibly can come into this ask, they're going to go move downstream. And by introducing a parallelism of 10, so you can see map async unordered 10, we have the ability to have 10 messages all out to actors at the exact same time. And then we're waiting for all those responses to come back. And as one comes back, it'll move downstream, and then we'll be able to pull another message in from the source. And implementing this is, a moment ago, we had an ask operator in our stream. Here, what we're going to do is we're actually going to use the question mark. And so that question mark is, so you can see actor question mark message. That's the actual syntax for doing an ask, and then we're mapping to the acknowledgement and then moving forward. So this is going to give you the ability to have many messages going out to many actors and going downstream. So far we've talked about, in this interop section, we've talked about how you can send messages to actors using a tell, how you can use streams to send messages to actors using an ask, and how we can increase that parallelism and be able to send messages to actors many at a time. But to flip that script, let's talk about how you, and this is really one of my favorite patterns in Akka. If you have an Akka actor, how do we get back into streaming world? If we have an actor that's received a message, and we want that actor to be able to now say, oh, well, I want that message to, be processed in this stream over here. How does an actor go about adding messages to a stream? There's a really great tool called a source.queue, and this queue gives you the ability to basically insert messages into a running stream. And so you can see in the code on the right, there's source.queue and there's integer. So the source.queue is going to be taking in messages of type int. And then we give it a buffer size, how many messages kind of sit in this buffer waiting to be processed. And then we have to give it a overflow strategy. If that buffer is full, how do we want this stream to respond? And so once we've initialized this stream, we can take this queue value that comes out of this initializing this source.queue, and we can use it within an actor to put elements into that stream. So all you have to do is do queue.offer, which return queue.offer, and then the whatever you're trying to put into the stream. So we're going to put in the element X, and then that is actually going to return a future. And in the case of the overflow strategy Backpressure, the minute that element is accepted into the stream, that future is going to complete. And so as long as you're using the overflow strategy Backpressure, there's only basically two options for that future. It can be incomplete or it can be complete. And so as long as it's incomplete, we're not, the actor is not going to put any more elements into the stream. And that now introduces backpressure from the stream into the actor. So the actor is basically getting a signal of whether or not it could put more work into the stream based on whether those features complete. And we'll talk about a different overflow strategy in a minute, but by taking all of these patterns that we've been talking about so far and implementing them together in a system, it starts becoming this really cool, fully back-pressured way of building a full application that takes advantage of many nodes. And so we can start introducing, let's say we have, another thing that Akka clustering gives you the ability to do is actually assign nodes specific roles. And in those roles, that they'll do specifically different things. So let's say we have an HTTP ingress node role and then a backend node role. So the backend node role does a lot of processing. The ingress really just accepts elements and then makes sure they're processed correctly. So we can build backpressure throughout both of these nodes, and then we can independently scale these things, both sides, up as needed. So if you need more HTTP nodes, we can just add those as necessary, and then we can add more backend nodes as those are necessary. And any of the front end HTTP nodes can communicate with any of the backend nodes, and vice versa. So we're able to introduce this really, really cool element of backpressure. We're able to take advantage of in-memory state with Akka sharding or distributed data. We're able to add and remove nodes that are able to still communicate and have a relationship with each other. And now all of a sudden our application starts feeling much more like an F1 car, being able to accelerate and decelerate and turn and handle all these different conditions. And as long as we're monitoring, we basically end up with our pit crew that's constantly keeping a view on every single little tiny detail about how our application is running. And then that pit crew can even start tuning things real time. So we can start thinking about this really cool scalable application as just a pool of resources. We've built this car, and we want to give it more front end network. We want to give more back end CPU, and we can start just adding nodes and removing nodes to get us the perfect ratio of front end network, front end CPU, and front end memory with the back end. And so this gives you really you can tune in, you can start dealing with all of these intricate details around really making the best possible application and making sure that it's able to give the best throughput, the best user experience at the most minimal operating cost. And this can be constantly dynamic and constantly changing. And you can even tune it in to auto scale with a lot of systems like Kubernetes or AWS. So regrettably, I have to inform everyone that at this point, I have one more concept that I think is super useful and super interesting that I've used on a couple projects recently, but the car metaphor absolutely falls apart for it. So one last car, love Aston Martins, they're super cool. But I promised that I would give you, for this Q.offer, one more, instead of doing Backpressure, there are some other kinds of overflow strategies. And one that I've used on a couple projects recently is really useful and really, really cool. So let's say in this situation, so we're using, we've got an e-commerce store, and it's Christmas or Black Friday or Cyber Monday, and everybody's checking out. I mean, people are buying things like crazy, and every time somebody checks out, so they've got their shopping cart actor, that's the actor on the left side, and they're trying to check out, and that needs to go through this checkout Akka stream. So they do an offer into the stream. The stream is going to go send a message, or it's going to, as it moves forward, it does this ML recommendations operation. And so it's going to feed the user back some recommendations of things they may want to buy, and before it lets them check out. Well, in the case of Backpressure, we're building a reactive system. We don't want to lose responsiveness just in the attempt to, upsell our customer. We want to be able to, given the resource constraints of this system, we want to recommend to absolute the most number of people that we can, but we don't want somebody to get a bad experience and just not check out because it's taking too long for the recommendation to come back. So in the case that we experience Backpressure, we want to go through the other way. So if all of a sudden a user is trying to check out and ML recommendations is overwhelmed, then we just want to go to a different source and direct them right to the checkout. But this pattern doesn't mean that we have to send everybody to skip ML recommendations. It basically just means that the ML recommendations will occur for the absolute maximum number of people that it possibly can. And then in the case that it's going to give a bad experience to one user, that user gets to check out without doing ML recommendations. So we're still able to maximize doing recommendations and upsell to customers, but no customer gets a bad experience just because our system might be limited on CPU or resources. And to implement this, it actually normally would be extremely complex pattern, but using this offer and Akka streams, it's extremely simple. I'm able to put all of the code that you would need to do this on this slide right here. So the biggest difference is you can see on the right side, the overflow strategy instead of Backpressure is drop new. And so now in the case that our buffer size is full in our source, rather than having a feature that doesn't complete, if the buffer size is full, that feature immediately, so you can see on the left, the options that actually come back are either in-queued or dropped. So basically, your message is either accepted into the queue and we're good and we all move on. Otherwise, if the message is dropped, it means that there's too much back pressure in that stream. And now our actor is going to send that message to the overflow path instead. And this is a really, really powerful tool when it comes to making sure that synchronous, so if you have like HTTP requests coming in or making sure that any kind of synchronous IO and something that might time out is able to blend in nicely with our back-pressured system. So, if the HTTP response is going to time out because we're waiting for the ML recommender to come back, we might as well just skip that, let them check out, and not time out that HTTP request. And this is how you'd go implement that. And when I said the car metaphor fell apart, it's because So this is a dam. It's a picture of a dam, and these are, every dam will actually have overflow valves. And so when the water level gets too high, it goes down this separate pipe. And so if the water's too high, we don't open up the dam and stop generating electricity. What we do is we just let all the extra water go around, and we still generate as much electricity as this dam could possibly generate. But anything that's excess gets to take a different path. And so it's the perfect metaphor for this drop new pattern, and I really like it, and certainly recommend that people take advantage of it. Well, we're right about at time. I'm happy to stay and answer questions if we've got any that have come in. But for those of you who are more interested in more of our technology or interested in more of some of this guidance, feel free to reach out to me. We've got a lot of cool products and open source tools at Lightbend, and there's some really cool things happening right now. So thanks a lot, everyone.
All right. Thank you, Nolan. A lot of the concepts in here are things that I've heard before, but, I would just want to say that you've described them in a different way that I've heard, and it makes a lot of sense. We do have time for a handful of questions, so let's jump right into that. Let's go straight to the heart of the matter. One question from our audience is, how do you handle consistent processing of streams across async boundaries? And what happens if a downstream operation fails?
It's an interesting question. I think there's, I'd love to ask some follow-ups to it, but let's say our application is, so when I think the person who's asking is saying consistent processing, that immediately in my head goes to an Akka actor. So we need to make sure, so an Akka actor or Akka sharding will make sure that only one operation is performed on any piece of data at any time. So let's say we have an Akka actor for a user. By putting that user data inside of an actor, we enforce consistency on it. So changes can only be made to it one at a time, and that enforces strong consistency. And so if I had a giant stream of data coming in, and I wanted to make sure that this application can be parallelized, but still wanted to make sure that user actor was consistent, that the pattern around just all of these messages coming in and then going out to the actor, that actor is still going to process all of those messages ordered one at a time and still guarantee consistency. And so that would be my being able to process messages in through a stream and send them over to an actor. That actor will guarantee that consistency and that only one change is made at a time.
The next question actually looks at the slide 29. If you could jump back one more. So the question refers to whether, if we're looking at this from a Akka cluster perspective, what happens to a message that's dropped if the destination is remote? So that's the phrasing of the question.
Yep. No, that's a great question. And this is something I thought about adding in here, but I thought it might be a little too extra. So in the case that there's a couple different situations that can happen. The message can get lost on the way out or on the way back in, or the actor could crash and something could go wrong there, or the node that actor is on could. So there's a lot of things that can go wrong. What's nice about this pattern is, so when you use an ask, you also have to set up a timeout. And if you don't get a response in a certain amount of time, you have to introduce the logic to respond to that. And so there's actor supervision strategies that you can set up that will be able to handle a lot of that stuff. So if this ask times out, this ask operation is actually going to fail. And then you can tell Akka streams how you want it to handle those failures. So potentially you could do something along the lines of, I want this ask to happen 3 times. And if it fails all 3 times, then I'm going to go forward the message into some sort of error queue or do some sort of handling on it. But if it's just a timeout, timeout could occur because the node went down. Maybe we're scaling up and that shard is moving from one node to another. There's a lot of reasons why that might happen. But you'd set up that failure logic in your stream, and then you'd have to also make sure that the messages that are going to that Akka actor are idempotent. And so, if that actor has already seen that message before, it's just going to respond with the ACK. But if it has, if it failed on the way there, as opposed to the way back, then it actually needs to process it.
All right, thanks for that. The next question refers to using this with Apache Kafka. So, for example, if we have two Kafka partitions in our source topic, how can we scale out to, for example, 10 or 20 parallel stream processors?
So that's actually a really good question. And it's something, for those of you, whoever's asking that question might also want to consider taking a look at Cloudflow, because there's some really cool things that Cloudflow does basically between Akka streams and Kafka. But the Akka streams Alpaca connector for Kafka has a couple of different ways of being able to, it's got a couple different source types that you can use when interacting with Kafka. And so one of those ways is that each source, I guess my mouse isn't, can you see my mouse, Oliver?
Yes.
Okay, so
can you?
Yeah, I can see it. It took me a minute.
Possibly not.
When this source shows up, when the source is initialized using Alpaca Kafka, it can either register as a member of a consumer group, so that source can get assigned multiple partitions to read. Alternatively, each node, there could be a stream initialized for each partition in your Kafka topic. That's another setting that's in Alpaca Kafka. So there's a lot of ways to kind of deal with this. The idea of reading in parallel from Kafka, and there's a lot of really nice tools in Alpaca Kafka to take care of that. But I should mention a really important thing when using a system like Alpaca, or using something like Kafka with streams, is if you're ever using map async, you need to use normal map async, not map async unordered. Because, typically when you're processing data from Kafka, you'll read it from Kafka, you'll do a bunch of work to it, that CPU heavy operation. And then in the sync, you'll commit the offset back to Kafka. So we'll say, okay, I've read the message, I did something to it, and now I'm telling Kafka that I finished processing it. If you ever do map async unordered with Kafka, you'll commit a higher number. You have the potential of committing a higher number offset back into the system. And in the case of failure, potentially work may not have been done. So ordering is extremely important within a specific partition in Kafka. So always make sure you use map async.
Boiling it down, always use map async.
Well, with Kafka.
I've got one more question before we've got to call it a day. It's actually about split brain resolver. So when split brain resolver is used and there's a network partition, what's the automated part of the recovery flow? Akka cluster isn't able to restart Kubernetes pods, for example, right? So what does split brain resolver, what part is automated? And then where does automation from another tool kind of pick up? Such as Kubernetes restarting pods when it recognizes,
Yep. Awesome question.
The JVM disappeared inside.
Yeah, so definitely one of the, using Kubernetes to restart pods and split brain resolver together really is one of those better patterns. Or there's other similar systems that do such things, but it's kind of funny what split brain resolver does is it it kills pods. And so in this diagram that I've shown here, you see these two nodes as red, but if there's a network partition, those nodes won't crash. They'll stay up and continue running. And from their point of view, all the other nodes crash, not them. And so what Split Brain Resolver does is it has all the strategy, all the logic in it for a node to be able to recognize whether it's on the wrong side of a network partition. So given that this line's happened, these two sides can't communicate with each other anymore. They, they're isolated, and their view of the world is only the other nodes that they're connected to. So from the side that's red, they'll think the other side went down, but Split Brain Resolver has the logic in it. So
in this case, we shouldn't perceive red as being down, but in fact, its own cluster of two nodes that doesn't see the three on the right side of the partition.
Right. You should see red as it's only down because Split Brain Resolver told it to go down.
Gotcha.
So yeah, Split Brain Resolver is the part that makes it red. Otherwise, you'll just have two independently running clusters that assumed that the other side crashed. And potentially, if you have like a service in Kubernetes that is still sending traffic to both sides, all of a sudden, actor for user one ends up on both sides of this, network partition, and half the traffic might end up on one side and half the traffic might end up on the other side. And so now all of a sudden you have two inconsistent versions of your user actor. And so that's what Split Brain Resolver does, is it actually automates the process of those pods recognizing that they're on the wrong side of a split brain, killing those pods, and then leaves it to Kubernetes to restart them. And hopefully when they come back up, the network partition is solved. Otherwise, Split Brain Resolver will take them down again.
Okay. Well, Nolan, this was a very interesting session. I hope that our attendees today enjoyed it. There were certainly some cool cars I should look into never being able to afford. And so thanks again for joining us and presenting today. As I said, folks, this recording will be made available to you in the coming week or two. So stay tuned for an email from us at Lightbend, and thanks to everyone for joining us today. Have a wonderful day. Bye-bye.